Two main factors determine whether a molecule containing an XH bond will behave as a Bronsted-Lowry acid or base. So section 13.9. The strength of the bond. It's going to help make sense of the bond strength for hydrogen halide acids and the polarity of the bond. So in our hydrohalix series, where we've got HF, HCl, HBr, and HI, right, the bond strength is weak between the HF and the H+. And you're also looking at the size. So the fluorine is the smallest and the iodine is the largest. So the bond strength is going to decrease. And as the bond strength decreases, the acid strength is going to increase because it's easier for you to pop this proton off, right? And popping that proton off makes it into an acid. Right? For an oxoacid, they contain something in the middle and then an O and an H. For a given series, so like phosphoric acid, right? H3PO4. For a given series, the acid strength increases with the number of oxygen atoms attached to it. So ClOH, Cl2H, right? Cl with 3 oxygens and hydrogen, Cl4H. So this is your hypochlorous, chloric, and perchloric acids. The greater the ability of X to draw electrons towards itself, the greater the acidity of the molecules, because this bond between this hydrogen and the molecule, if all the electrons are getting pulled towards these oxygens, it means that the electron density is moving away from the hydrogen towards those other oxygens, and this bond gets progressively weaker. Right. So looking at a series of these, for our oxoacid HClO4, the Ka value is going to be really large. For HClO3, it's pretty much equal to 1, which is still very large. For HClO2, it's going to be 1 times 10 to the minus 2. So this is a pretty strong, but it's still technically a weak acid. Right? If I'm looking at H2SO4, it's pretty much infinite for pulling this one proton off. And then we saw that this second one was like times 10 to the minus 2. That's pretty large. Our H2SO3, which only has 3 oxygens, is going to act like a weak acid. Right? Our nitric acid is going to have a large. Right? It's going to be a strong acid. And our HNO2 with only 2 oxygens is going to be a weak acid. So comparing the electronegativity of X and Ka for a series of these oxoacids, we can look at, well, what happens if we keep the oxygens the same and we change what the guy in the middle is. Right? So chlorine, bromine to iodine. The electronegativity of chlorine is greater than that of iodine, and the Ka for the chlorine is going to be larger than that for the iodine.